Tonight, we're going to place our entire galaxy next to the structure that actually contains it. The Milky Way is a spinning disk of stars, gas, and dust, home to everything we've ever seen with the naked eye, every constellation, every star system that's ever been named or mapped. From the inside, it feels like the whole of existence. It's the backdrop to every night sky anyone has ever looked up at, the source of every point of light we've learned to recognize. And yet, against the true scale of the universe, our galaxy is a much smaller piece of the picture than anything you can imagine. By the end of tonight, you're going to understand exactly how small our galaxy really is, how it fits inside groups, clusters, superclusters, and finally the observable universe itself, and why the true size of everything that exists might be a number we can never actually know. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something familiar. Stand outside on a clear night, somewhere dark enough that you can actually see the sky, and look up. There's a faint band of light cutting across the darkness from horizon to horizon. That band is the Milky Way. Not the whole Milky Way, because you're inside it. What you're seeing is the combined glow of billions of stars, so distant they merge into a single wash of light. The disk of our galaxy, seen edge-on from within. Now, the Milky Way is what astronomers classify as a barred spiral galaxy. It has a flat disk of stars, gas, and dust, wound into sweeping spiral arms that wrap outward from the center. At the heart of the galaxy is a dense central bulge where stars are packed together so tightly that a planet orbiting near the core would never experience full darkness. Even at night, the sky would glow. Running through that bulge is a long, elongated bar of stars, a structure that extends across the central region before the spiral arms peel away from its ends. That's the barred part. And at the absolute center of everything, the gravitational anchor of the entire galaxy, sits a supermassive black hole called Sagittarius A. Its mass is roughly 4 million times the mass of our Sun. 4 million solar masses, compressed into a region smaller than the orbit of Mercury. The disk of the Milky Way spans about 100,000 light-years in diameter. Some measurements push that number a bit higher, to around 120,000 light-years, depending on where you define the outer edge of the most distant spiral arms. The disk is also extraordinarily thin relative to its width, only about 1,000 light-years from top to bottom in its densest regions. So, you have a structure that's roughly 100 times wider than it is thick, a dinner plate, scaled up to galactic proportions. Our Sun sits about 26,000 light-years from the galactic center. That puts us slightly more than halfway out from the core to the visible edge. Not at the center, not at the edge. We're in the suburbs. The Sun orbits the galactic center at about 500,000 miles per hour. At that speed, one complete orbit takes approximately 225 million years. Astronomers call this a galactic year, or a cosmic year. In the entire history of complex multicellular life on Earth, our Sun has completed roughly 2 full orbits of the Milky Way. Over its entire 4.5 billion year lifetime, it's only gone around about 20 times. The Milky Way contains somewhere between 100 billion and 400 billion stars. The range is wide because counting stars inside our own galaxy is genuinely difficult. We can't step outside and photograph the whole thing. We're embedded in the disk, surrounded by gas and dust that blocks our view in many directions. Dense clouds of interstellar dust absorb visible light entirely, hiding entire regions of the galaxy from optical telescopes. Infrared observations, which can see through dust that blocks visible wavelengths, have gradually expanded our census of the galaxy. But even with infrared, the mapping is incomplete. The lower estimate of 100 billion stars is already almost beyond the range of numbers our minds were built for. If you counted 1 star per second, without sleeping, without pausing, it would take you over 3,000 years to reach 100 billion. And most of those stars would be red dwarfs, dim and small, but burning for trillions of years. Some of the red dwarfs in the Milky Way today formed when the universe was young. They were there before our sun existed. They'll still be burning when our sun is gone. The Milky Way is not just enormous in space, it's enormous in time. Its oldest stars are over 13 billion years old. Its formation began shortly after the Big Bang itself. The observable universe is not the same thing as the universe. The universe itself, as best as we can determine, has no physical edge. There is no wall, no boundary, no place you could travel to and declare that this is where the universe ends and something else begins. What we call the observable universe is a different concept. It's the portion of everything that exists from which light has had enough time since the beginning to reach us. The universe is 13.8 billion years old. Light travels at a fixed speed, about 186,000 miles per second. So the furthest light that could have possibly reached us by now left its source when the universe was extremely young. Anything further away than that, light from it is still traveling toward us. It hasn't arrived yet. The sphere, defined by that limit, the sphere centered on Earth, within which light has had time to travel to us, is what we call the observable universe. Everything inside that sphere is, in principle, something we could observe with the right instruments. Everything outside it is, for now, beyond our reach. Not because it doesn't exist, because its light hasn't had 13.8 billion years to get here yet. Now, you might expect the radius of that sphere to be 13.8 billion light years, the age of the universe in years, times the speed of light. But the actual radius of the observable universe is about 46 billion light years. Not 13.8 billion. 46 billion. The reason for this discrepancy is one of the more mind-bending facts in cosmology, and it comes down to what space has been doing the entire time that light has been traveling. Space has been expanding. When a distant galaxy emitted light 12 billion years ago, that galaxy wasn't 12 billion light years away. It was much closer. But as the light traveled toward us, the space between us and the galaxy was stretching. The galaxy was being carried further away by the expansion of space, even as its light was crossing the decreasing gap. So when that light finally arrives, the galaxy that sent it is now much further away than the distance light could have crossed in the time available. It's as if you're trying to catch someone running away from you, and the ground itself is stretching beneath your feet. The light catches up because it was emitted when the runner was close enough. But by the time it arrives, the runner has been carried much further by the expanding ground. When you account for all of this, the most distant light we can observe today was emitted by sources that are currently about 46 billion light-years away from us. The observable universe has a radius of 46 billion light-years, a diameter of about 93 billion light-years. Now, set that next to the Milky Way, 100,000 light-years, versus 93 billion light-years. To get from one number to the other, you multiply by about 930,000. The observable universe is 930,000 times wider than our galaxy. There is no everyday analogy that fully captures what that means. The gap is too large for comparisons that stay within the range of human experience. What matters is understanding that the Milky Way, for all its hundreds of billions of stars, is a microscopic participant in a structure that outscales it by nearly a factor of 1,000,000. The galaxy isn't a uniform disk of evenly distributed stars. It has layers, different populations of stars living in different regions, each telling a different story about how the galaxy formed and evolved. The most visible and densely populated region is the thin disk. This is the flattened midplane of the galaxy, where the spiral arms are found, where the gas clouds are densest, where new stars are forming right now. Young stars live in the thin disk. Hot blue stars, recently ignited from collapsing molecular clouds, burning bright for only a few million years before they end their lives in supernovae. Open clusters, loose associations of a few hundred to a few thousand stars that form together from the same cloud and are still drifting through space near each other. And the molecular clouds themselves, dense regions of cold gas and dust, where the next generation of stars is already taking shape. The Orion Nebula, about 1,400 light-years from us, is one of the most spectacular examples visible from Earth. A vast cloud of gas and dust, lit from within by newly formed hot stars, with planetary systems assembling in its darker, cooler regions. Stars like our Sun may have formed in something similar 4.5 billion years ago. Beyond the thin disk is the thick disk. Older stars, more metal-poor, orbiting the galactic center on paths more inclined to the plane of the galaxy. These stars belong to an earlier era of the Milky Way's history, when the galaxy was younger and its shape less settled. They carry chemical signatures in their spectra that reflect the composition of the universe at the time they formed, before stellar generations had enriched it with heavy elements. Above and below the disk is the galactic halo, a roughly spherical region surrounding the entire galaxy. The halo extends tens of thousands of light-years above and below the disk and contains far fewer stars than the disk itself, maybe 1% of the galaxy's total stellar mass. But the stars in the halo are among the most ancient in the entire galaxy. Population 2, stars, as they're classified, formed when the universe was young and the chemical environment was almost pure hydrogen and helium. These stars are red and dim and old. They've been burning quietly for over 10 billion years. They were there before the solar system existed, before Earth existed, before the Sun existed. Many of these halo stars are gathered into globular clusters, dense spherical collections of hundreds of thousands of stars, packed into regions just tens of light years across. If you could stand on a planet inside a globular cluster, the sky would be dazzling. Stars, within a few light years in every direction. The Milky Way has about 150 known globular clusters. They orbit the galactic center on sweeping paths that carry them through the halo and sometimes through the disk. Some are thought to be the remnant cores of ancient dwarf galaxies that the Milky Way absorbed long ago. The gravity of our galaxy stripped away their outer stars, leaving only the densely packed cores. Globular clusters are among the most useful objects in astronomy. Their ages set a lower limit on the age of the universe itself. If a globular cluster is 12 billion years old, the universe must be at least that old. Early measurements of globular cluster ages in the 1990s produced a historical curiosity. They seemed to be older than the universe, as estimated at the time. That pointed to errors in the measurement of the Hubble constant, the rate of cosmic expansion. Resolving the discrepancy required improving the distance measurements to nearby galaxies, which in turn led to a better value for the expansion rate, which led to the current best estimate of the universe's age at 13.8 billion years. The age problem is now resolved. Globular clusters are old, but the universe is older. Beyond the halo of visible stars is the dark matter halo, a vast, invisible structure extending far beyond anything you can see. The dark matter halo of the Milky Way is thought to reach out to somewhere between 500,000 and 600,000 light-years from the galactic center, 6 times the diameter of the visible disk. The dark matter halo is roughly spherical, enveloping the galaxy in all directions. Dark matter particles pass through everything constantly. Through the disk, through the stars, through your body as you read this. But because dark matter interacts with normal matter only through gravity, not through electromagnetism, not through the strong or weak nuclear forces, it passes through without any detectable interaction. We know it's there because of what it does to the stars we can see. The outer stars of the Milky Way orbit at speeds that only make sense if there's far more mass present than the visible stars and gas can account for. The dark matter holds them in. It is, in a very real sense, the skeleton of the galaxy. The visible stars and gas are the skin. The dark matter is the framework underneath. So the Milky Way is not just the 100,000 light-years of the visible disk, including the dark matter halo. It extends to 600,000 light-years in all directions. Still small compared to the observable universe, but larger than it first appears. The Milky Way is not alone in space. It belongs to a local family of galaxies called the Local Group. The Local Group contains about 80 galaxies in total, most of them dwarf galaxies, small collections of a few billion stars that orbit around the larger members. The 3 largest members are the Milky Way, the Andromeda Galaxy, and a smaller spiral called the Triangulum Galaxy. Andromeda is approximately 2.5 million light-years away. It's the most distant object visible to the naked eye on a clear, dark night, a faint oval smudge of light in the constellation Andromeda. When you look at it without a telescope, the light entering your eye left Andromeda 2.5 million years ago. You're seeing it as it was when our ancestors were making the earliest stone tools. Andromeda is a large spiral galaxy, similar in overall structure to the Milky Way. By some measurements, it's slightly more massive. By others, roughly comparable. It has its own supermassive black hole at its center, and its own population of hundreds of billions of stars. It also has its own retinue of satellite galaxies, and its own dark matter halo. And it is heading toward us. The Milky Way and Andromeda are moving toward each other, pulled by mutual gravity, at about 250,000 miles per hour. At that rate, they will begin to interact in about 4.5 billion years. The merger will be slow and gradual, unfolding over hundreds of millions of years. It won't look like a dramatic collision. Stars are too spread out relative to their sizes for many of them to physically strike each other. The interaction is gravitational. Long tidal streams of stars will be torn from both galaxies as they pass through each other. Spiral arms will be disrupted. Gas clouds in both galaxies will be compressed by the collision, triggering bursts of new star formation. Over the course of hundreds of millions of years, the galaxies will pass through each other, then be drawn back together by gravity, then pass through again. Eventually, after a series of passes and interactions, they'll settle into a merged structure, not a spiral galaxy any longer. The rotation and structure that defines spirals will have been scrambled by the interaction. The result will be a large elliptical galaxy, rounder, smoother, full of older stars with no ongoing star formation. Astronomers call this future object Milkomeda, or sometimes Milkdromeda. Our Sun will survive the merger. It will simply end up in a different orbit around the merged galaxy's center. The night sky from any planets orbiting the Sun in that era will look completely different from what it does now. But it will still have a sky full of stars. The Magellanic Clouds are among the most prominent members of the local group after Andromeda and Triangulum. The Large Magellanic Cloud sits about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years away. Both are visible from the southern hemisphere as fuzzy patches of light that look like detached pieces of the Milky Way. They are satellite galaxies, gravitationally bound to us and orbiting our galaxy over timescales of billions of years. The Milky Way's gravity is actively disrupting both of them. There's a structure called the Magellanic Stream, a long trail of gas being pulled out of the Magellanic Clouds by our galaxy's tidal forces, arcing across about 140 degrees of the southern sky. Over billions of years, both the large and small Magellanic Clouds will likely be absorbed into the Milky Way. Their stars and gas added to our galaxy's own reserves. The Milky Way has almost certainly done this many times before. There are stellar streams in the halo, long arcs of stars with similar ages and compositions that are the remnants of dwarf galaxies absorbed long ago. The Sagittarius dwarf, spheroidal galaxy, is in the process of being absorbed right now. It has already passed through the Milky Way disk multiple times, and stars torn from it trail behind it in a stream that wraps around the entire galaxy. Our galaxy grows by consuming smaller ones. It's been doing it since the beginning. The entire local group, with all its 80 galaxies, spanning about 10 million light-years, is the home neighborhood. 10 million light-years, 100 times the diameter of the visible Milky Way disk. And the local group is itself just one small component of a much larger structure. The Virgo supercluster spans about 110 million light-years. At its center sits the Virgo cluster itself, a dense concentration of over 1,000 galaxies, about 50 million light-years from us. The Virgo cluster is dominated by several enormous elliptical galaxies. The largest, Messier 87, contains several trillion stars. Several trillion. Its total mass is about 50 times the mass of the Milky Way. At its center sits a supermassive black hole with a mass of approximately 6.5 billion times the mass of our Sun. To put that in context, the black hole at the center of our own galaxy has a mass of 4 million solar masses. The black hole at the center of Messier 87 has a mass of 6.5 billion solar masses. It is over 1,000 times more massive. Its event horizon is so large that the entire planetary solar system, out past the orbit of Neptune, would fit inside it. In 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole. The black hole they imaged was the one at the center of Messier 87. The Event Horizon Telescope is not a single telescope. It's a global network of radio telescopes spread across multiple continents and in multiple countries. From Hawaii to Chile to Greenland to Spain to Antarctica. By combining observations from all these instruments simultaneously, using the rotation of the Earth to build up a picture over time, the collaboration created a virtual telescope with an effective diameter equal to the diameter of Earth. That's the angular resolution needed to image a black hole 50 million light-years away. The resulting image showed a dark, circular region, the black hole's shadow, surrounded by a bright ring of glowing, superheated gas. That ring is material orbiting the black hole at nearly the speed of light. The temperature of that material is billions of degrees. Nothing in that ring survives long. It spirals inward and is consumed. Messier 87 also has a jet, a beam of matter and energy shot out from near the black hole at nearly the speed of light. That jet extends for about 5,000 light-years into the surrounding intergalactic space. It's made of electrons and positrons and magnetic fields, all accelerated to relativistic speeds by the black hole's enormous gravitational and electromagnetic fields. When those particles slam into the surrounding gas, they produce enormous lobes of radio emission visible across hundreds of thousands of light-years. The Virgo cluster contains over 1,000 galaxies like Messier 87, each with its own internal structure, its own black holes, its own stellar populations. The environment is violent. The space between galaxies in the Virgo cluster is filled with hot gas at temperatures of tens of millions of degrees. It's invisible to optical telescopes, but it glows brightly in X-rays. When a galaxy falls into the cluster at high speed, this hot intergalactic gas pushes against the infalling galaxy's own gas. The effect is called ram pressure stripping. It's powerful enough to pull the star-forming gas right out of a galaxy as it moves through the cluster. Stripped of its gas supply, the galaxy can no longer form new stars. Its existing stars age and fade. Over billions of years, the galaxy becomes red and dead, full of old stars, incapable of renewal. Many galaxies in the Virgo cluster, and in clusters like it around the universe, show exactly this signature. Red, quiescent. Their star formation ended the moment they fell too deep into the cluster's gravitational well. The Milky Way is not in such an environment. We're in the quiet outskirts of the local group. But gravity doesn't stop at the boundary of the local group. We're being pulled toward the Virgo cluster by its gravity. The entire local group is falling toward Virgo at about 140 miles per second. We're not going to get there. The acceleration of the universe's expansion will eventually carry the Virgo cluster beyond our cosmic horizon, faster than we can fall toward it. But the pull is real, and it's been shaping our trajectory through space for billions of years. In 2014, a team of astronomers announced a discovery that fundamentally changed how we understand where the Milky Way sits in the large-scale cosmos. The team was led by Brent Tully at the University of Hawaii. They had been painstakingly mapping the velocities of thousands of galaxies across a vast volume of space. Not just the velocities caused by the expansion of the universe, which carries every galaxy away from every other. They were mapping the additional peculiar velocities, the extra motions caused by the gravitational pull of nearby mass concentrations. Every galaxy in the universe has two components to its motion. There's the component from cosmic expansion, which pushes everything apart. And there's the component from local gravity, which adds motion toward the nearest concentrations of mass. By carefully subtracting out the expansion component, you're left with the peculiar velocities. And peculiar velocities tell you where mass is. They tell you which way things are being gravitationally pulled. Tully's team measured the peculiar velocities of over 8,000 galaxies. They found something remarkable. A huge volume of space, extending about 500 million light-years in all directions, was filled with galaxies, all sharing a common flow. They weren't just moving apart due to expansion. They were all flowing in the same direction, toward the same gravitational basin. Every galaxy in this enormous region was being pulled toward the same sink. That shared gravitational basin defined a coherent structure. Not a visible structure in the photographic sense. You couldn't just look at the sky and see its edges, but a structure defined by motion, by the gravitational influence it exerts on everything in its vicinity. Tully's team called it Laniakea. The name comes from the Hawaiian language. Lani means heaven. Akea means spacious or immeasurable. Immeasurable heaven. Laniakea contains about 100,000 galaxies. It spans about 500 million light-years. Our galaxy sits near its outer rim. Laniakea is 5,000 times the diameter of the Milky Way. The gravitational center toward which all those galaxies are flowing is a region called the Great Attractor. It sits about 250 million light-years from us. For decades, astronomers knew something massive was pulling on our galaxy and everything nearby. The motion was measurable, but the source was hidden. The Great Attractor lies in a direction on the sky that happens to coincide with the plane of the Milky Way's disk. All the dust and gas in our own galaxy's midplane blocks our view in that direction. The region even has a name in astronomical cartography: the zone of avoidance. Not because astronomers don't want to look there, but because our own galaxy is in the way. Only in recent decades, with the use of infrared and radio wavelengths that can penetrate the dust, has the picture become clear. The Great Attractor is not a single object. It's a complex of galaxy clusters, with the Norma cluster at its heart. The combined mass of the whole system is equivalent to tens of thousands of Milky Way galaxies. But even the Great Attractor isn't the ultimate source of the flow. Beyond it sits the Shapley concentration, a supercluster of galaxy clusters about 650 million light-years from us. It contains over 8,000 galaxies and has a mass of roughly 10 million billion times the mass of the Sun. The Shapley concentration is one of the most massive structures in the observable universe within the range we can map precisely. And Laniakea itself is being pulled toward it. Everything flows. The Milky Way is being pulled toward the local group's center. The local group is falling toward Virgo. Laniakea as a whole is being drawn toward the Shapley concentration. Structure upon structure, each pulling on the next. We're not stationary in the cosmos. We're participants in a vast gravitational choreography. Zoom out further still, and the individual structures, the clusters, the superclusters, dissolve into pattern. At the largest scales, the universe has an architecture. It's called the cosmic web, and it's one of the most striking things that cosmology has revealed. The cosmic web is the name for the overall large-scale structure of matter in the observable universe. At scales of hundreds of millions to billions of light-years, matter is not uniformly distributed. Galaxies are not scattered randomly through space, like stars in a galaxy. They're gathered into long, thin filaments, stretching across hundreds of millions of light-years. These filaments intersect at dense nodes called galaxy clusters. Between the filaments are vast, nearly empty regions called voids. When you look at computer simulations of the cosmic web, or at actual three-dimensional maps constructed from galaxy surveys, the appearance is striking. The structure looks biological. It resembles neural tissue, or the inside of a sponge, or the arrangement of foam bubbles. Thin threads of matter connecting at points of concentration, with dark, empty cavities stretching between them. It's a structure so elegant that it almost looks designed. It isn't. No designer arranged the cosmic web. The structure emerged naturally, from initial conditions set in the first tiny fraction of a second after the Big Bang, amplified over billions of years by gravity alone. In the very earliest moments of the universe, matter was distributed almost perfectly uniformly. But almost is the key word. There were tiny fluctuations in density, regions that were fractionally denser than their surroundings. These fluctuations had quantum mechanical origins. In the era of inflation, a period of extremely rapid expansion that occurred in the first fraction of a second after the Big Bang, quantum fluctuations in the energy field driving the inflation were stretched from subatomic scales to cosmic scales. They became the seeds of structure. After inflation ended, those seeds began to grow. Over hundreds of millions of years, and then over billions, gravity drew matter toward the denser regions. Dense regions attracted more matter, becoming denser still. Less dense regions shed their matter as gravity pulled it away, becoming emptier still. The denser regions connected into filaments. The emptier regions expanded into voids. The nodes where filaments intersected became the massive galaxy clusters. Over the full age of the universe, from the Big Bang to today, this process produced the cosmic web we observe. The first systematic evidence for the web came from galaxy surveys in the 1980s. At the time, astronomers had expected galaxies to be distributed roughly randomly through space. Maybe a little clustering here and there, but nothing organized on truly large scales. What they found was the opposite. Galaxies were arranged in sheets and walls, surrounding enormous empty bubbles. The CFA Great Wall, discovered in 1989, was a filament of galaxies about 500 million light-years long. Later, the Sloan Great Wall was mapped in 2003, stretching about 1.37 billion light-years across. And then, in 2013, astronomers announced the discovery of the Hercules Corona Borealis Great Wall. Its estimated size is staggering, somewhere between 6 and 10 billion light-years in extent. If the larger estimates are accurate, it represents a single coherent structure spanning roughly 1/10 of the diameter of the entire observable universe. One structure, 10 billion light-years. To put it in terms of the Milky Way, the Hercules Corona Borealis Great Wall is approximately 100,000 times the diameter of our galaxy, not the observable universe, not the full cosmic web. One filament within it. 100,000 Milky Ways laid end to end. The cosmic web gives us the large-scale map of where the universe put its matter. The answer is mostly into thin structures surrounding enormous cavities. The voids are not small features. The Botez void is about 330 million light-years across. It contains almost no galaxies. A few scattered dwarf galaxies, isolated in a near-empty bubble. When it was discovered in 1981, it caused genuine surprise. The void was so large that it was hard to reconcile with existing models of how structure forms. At the time, the size seemed almost impossible to explain. Better models, driven by better data on dark matter and the evolution of the cosmic web, have since explained it. The voids are where matter used to be, before gravity drew it into the filaments. They're the complement of the filaments. Where filaments are the overdense regions that attracted matter, voids are the underdense regions that lost it. And they are, by volume, the dominant feature of the universe. If you placed yourself at a random point in the observable universe, not choosing where you land, just a truly random position, the odds are that you'd find yourself in a void. Most of the volume of the observable universe is void. Galaxies are clustered into the thin web of filaments that occupies a small fraction of the total volume. Everything else is a vast, dark, near emptiness. Our galaxy happens to sit not in a void, but in a region of modest density. The local sheet, as it's called, is a relatively flat arrangement of galaxies, including the Milky Way and its nearby neighbors. Not in a dense cluster like Virgo. Not in a void. In between. Which turns out to be a reasonably comfortable place to be, at least for the formation and stability of a planetary system over billions of years. Dense cluster environments can disrupt planetary systems through gravitational interactions and high-energy radiation. Voids are too sparse in gas and heavy elements for complex chemistry to develop quickly. The suburbs of a filament, near a modest group of galaxies, may be a particularly suitable environment for the development of complex systems like planetary biospheres. Whether this has anything to do with why life exists here, or whether it's coincidence, is an open question. The number of galaxies in the observable universe is one of those figures that was dramatically revised upward in the recent past. And the revision itself tells us something important about how we study the cosmos. Before 2016, the standard estimate was somewhere around 200 billion galaxies, a large number. But it had been arrived at by measuring the density of galaxies in observed patches of sky and extrapolating to the full volume of the observable universe. The problem was that older instruments had detection limits. Small, faint, distant galaxies, the kind that form early in the universe's history, were too dim to detect in earlier surveys. The count was based only on what had been seen, not on what was actually